We are the Triangle Biobuilder Club, consisting of high school freshmen and sophomores coming from the Triangle region of North Carolina. We've designed a yeast that can produce a customizable antimicrobial spider silk bandage with wound healing properties.
Wound infections, chronic wounds, surgical site infections, and unnecessary scarring impact millions of people worldwide. Since half the world lacks access to basic health care, these conditions can be fatal. In response, we designed a portable ointment containing a modified yeast that, when applied to a wound, will create an antimicrobial bandage made of piriform spider silk. The bandage is created in areas with sufficiently high enough levels of reactive oxygen species and low enough levels of oxygen. The combination of yeast, piriform silk, and antimicrobial human beta-defensin 3 creates a self-assembling, strong, flexible, biodegradable antimicrobial bandage that is customized to the wound shape and responsive to the wound environment. Opposed to traditional bandages, using a living system allows the silk to grow into a perfect fit for each wound, but used on serious wounds without the supervision of a medical professional, biodegrade and sustain cleanliness instead of the continuous need to change or remove the bandage, and add additional properties to the spider silk to assist the body with healing. Currently, antimicrobial properties were chosen. Self-manufacturing by yeast reproduction will provide a cheap and accessible option. This will also be much more portable and easier to transport. Our design is comprised of two systems controlled by the same modified A and B1 promoter. One system results in silk creation, while the other results in antimicrobial HBD3 production. The A and B1 promoter will be modified by the addition of the CACG motif and ARE enhancer.
The chassis for our design is the Saccharomyces cerevisiae yeast. It can be easily transformed, allowing for deletion or addition of new genes, and it's better than bacteria at producing large proteins like the piriform spider silk proteins in great quantities. The Y55 strain was chosen because it has been identified as avirulent, unlike other strands that have been known to cause infection in humans.
Two key advantages that this spider silk bandage has over traditional bandages are its ability to grow to fit the shape of the wound and its ability to grow in times of critical need. The bandage is able to morph to the shape of the wound because the system responds to high levels of ROS. ROS are imperative to wound healing, and their levels increase significantly at a wound site, so they can be used to determine which cells are being affected by a wound and which are not. Then the bandage will grow to encompass only the region of the wound and therefore fit its shape. In addition, the system also responds to low levels of oxygen. Under anaerobic conditions, meaning that oxygen is low, the system will be activated. This is imperative because under anaerobic conditions at a wound site, the body's natural healing processes are inhibited. Therefore, this silk bandage will be able to assist the healing when the body is in its weakest state.
The strength, elasticity, toughness, and biocompatibility have made spider silk a valuable material in many biomedical fields. Bandages are just one of many future applications. Since each spider produces up to 7 types of silk, we decided on A. argentatus piriform silk to be excreted to form our bandage. Piriform silk, the sticky silk used to attach to substrates, is relatively unexplored compared to dragline silk, but has several properties beneficial to wound healing. These properties include adhesion to skin, crack defense, elasticity, stress distribution, an extreme strength-to-weight ratio, biodegradability, and support of self-assembly. It is excreted as a liquid, but quickly solidifies into an immovable monoblock. The expression of the PYSP1 gene will create the silk spidroids. This expression is enhanced by the CACG motif part of the promoter. This gene contains a signal peptide to ensure excretion. Once excreted by the yeast, the silk will self-assemble and eventually biodegrade as the wound heals due to wound healing enzymes.
Antimicrobial and wound healing properties can be added by inserting the gene DEFB103B to code for the production of human beta-defensin 103B or HBD3. The HBD3 induces secretion of the cytokine IL-17, normally found in human skin, but the beta-defensin would increase its secretion. When IL-17 is secreted, it induces AMPs, or antimicrobial peptides, that are already present in epithelial cells but increases their effectiveness. These AMPs inhibit bacteria and microbe growth while promoting wound healing in skin.